In our green and pleasant land, we do not lack for rain. It falls on the fertile soil to give life to our crops. More than enough for the needs of the land, the precious water percolates beneath the ground, emerging as springs and flowing on in ditches and streams. It fills the rapid shallow brooks, deep flowing streams, rivers where fishes glide. It feeds our lakes and rivers which wind down to the sea. From there, the clouds are drawn back into the sky to fall again as rain, making the cycle complete. But man intervenes in this natural cycle. Where there were fields drinking in the rain, man spreads out buildings and roadways, from which the water must now run off, carrying with it traces of pollution. To satisfy his needs, water is gathered into reservoirs, or is collected from wells, lakes, and rivers. It is then purified to a high degree, piped to our homes and our factories. Here we treat it lightly, for it seems so cheap and plentiful. It is disposed of so easily when we have finished with it. We use it in colossal quantities for our industrial processes. As man's standard of living rises, he calls for more and more water, the amount growing at an estimated rate of 3% each year. Although quantities vary from place to place and year to year, every person accounts for about 250 to 300 litres of water per day. The equivalent of a bath of water, carrying dirt, waste matter, grease and chemicals, the waste products of our civilization, domestic and industrial, goes down the drain every day for each man, woman and child. It seems so easy to dispose of, but where can it go? Only back into the natural cycle from which it was taken. From the house, the sewage passes through drains and along sewers of larger and larger size buried beneath the city streets. On its way, it is joined by liquid waste from industry. All this sewage, together with the polluted rainwater from our roofs and roads, has to be returned to the streams and rivers where it will be diluted and where nature herself will do her best to purify it. The pollution is, however, so great that without help, nature is unable to cope with it. Reserves of oxygen which the river carries become used up, and oxygen needed for the river's own life is also taken. Fish die, the river stagnates. In times of heavy rain, emergency overflows on the public sewers have to operate, so allowing pollution to enter the river. Unsightly and undesirable as this is, it is at least only occasional. Only with proper water pollution control can the bulk of sewage receive purification, safeguarding our rivers, which will increasingly be required for water supply. Using nature's own methods, speeded up many times by man's ingenuity, the pollution load on the river can be limited to an amount with which the river can safely deal. Day by day, the large volumes of sewage from our homes and industry are purified in a number of stages. First, the floating matter must be divided and shredded to protect machinery. Next, the heavy particles of road grit and sand, which would cause excessive wear in machinery and block pipes and channels, must be removed. And provision must be made for the temporary storage of storm water. Thirdly, most of the lighter organic particles in suspension must be settled out. At the fourth stage, biochemical changes are encouraged to break down the pollution which remains in solution and suspension, and the waste products of this process settled out. The last stage is to dispose of the solid matter from the third and fourth stages. What changes can be looked for during the treatment? Crude sewage must have its content of suspended solids reduced by at least 90%, and its 5-day biochemical oxygen demand by at least 95% before the final effluent can be safely discharged to the watercourse. These reductions will have been obtained in a much shorter time than nature alone can achieve. Let us follow the treatment through. Floating matter must first be removed from the flow, for without this precaution, pumps would choke and pipes would block. Therefore, in one method, as the sewage reaches the works inlet, it is led towards the screen house and through the screens, which can be automatically operated and cleaned. The screenings can be passed to a macerating pump, which chops the material to fine pieces before returning it to the flow. These two functions of screen and macerator can be combined into one unit in the comminutor, where, as the drum rotates against fixed blades, the solid particles are shredded between hardened steel cutters until they are small enough to pass through the slots. In order to reduce blade wear, this machine is sometimes used after the process which we look at next. The removal of heavy inorganic particles is made easier by the fact that such particles settle very quickly, very much more quickly than the lighter organic particles which account for much of the pollution. The problem is, however, complicated by the large variations in rates of flow which can take place. By adopting channels of approximately parabolic cross-section, the velocity of flow can be kept substantially constant, whatever the depth of flow. In a suitable length of channel, all the grit has time to settle out and is dredged out at intervals. In another design, the detritor, the flow is made to pass evenly across a square tank controlled by an outlet weir. The grit, accompanied by some organic matter, settles to the floor and is removed by a rotary scraper to a washing channel. The organic matter is returned to the main flow with the wash water. And the nearly clean grit is discharged. So far, all the sewage which reaches the works has been treated. Because in storm time the rate of flow increases to several times the rate in dry weather, it is convenient to pass all rates of flow in excess of 3 times the dry weather flow over a storm overflow weir to storm water storage tanks. After the flow rate has fallen, these tanks are emptied and the content returned for full treatment. If, however, the storm continues, settled sewage is passed to the river. The removal of much of the organic suspended matter from sewage could be achieved in an hour or two with static settlement. seen here on laboratory scale in an Imhoff cone. When dealing with millions of gallons of sewage per day, this static settlement is impracticable, and the system has to be a continuous one. By passing the sewage gently through large tanks, a process taking a few hours, most of the organic pollution settles out as sludge and is scraped by a slowly moving blade to a hopper from which it is removed at intervals. Tanks are not only made rectangular in shape, they can be circular with radial flow, or deep tanks with upward flow. All make use of the sedimentation principle, and from them the settled sewage passes over a weir to the next process. At this stage, the suspended solids content has been reduced considerably, from 350 to 90 milligrams per litre, but the biochemical oxygen demand, BOD, only from, say, 400 to about 270 milligrams per litre. The major reduction in BOD is to be made in the next stage, the biological treatment. One method of biological purification is the bacterial filter. The familiar circular bed is fed through radial arms, through which settled sewage is distributed evenly over the surface. An important factor is good ventilation. Rectangular filters with travelling siphon pipes are used to economize in land area on larger installations. These are not real filters. The stones provide surface area to which a gelatinous film can cling. In this, aerobic organisms thrive in conditions of good ventilation, mild temperature, and adequate food supply, as the settled sewage trickles past at the most efficient rate. A balanced biological system exists. Bacteria break down the complex organic matter, protozoa feed on the bacteria and debris, and algae feed on soluble matter, while scouring organisms such as larvae and worms help to keep the voids open. The waste products of the bacterial action must be removed in a further sedimentation process before the final effluent can be passed from the works in a stabilized form suitable for discharge to the river. The humus, a brown sludge with a high water content, is drawn off and returned for treatment with the crude sewage. Biological treatment can also be carried out in activated sludge processes, in which aerobic organisms are introduced to the tank effluent by returning humus-like sludge from the final settling tanks and providing plenty of air, good mixing, and a longer time of contact. Here again, bacteria and protozoa play active parts. In the Sheffield system, air is repeatedly introduced at the surface by paddles, as the mixture of tank effluent and activated sludge flows through miles of channel. The simplex surface aeration process uses deeper tanks, and mixing is effected by a central rotating cone. The mixed liquor of sludge and sewage is drawn up the central uptake tube and discharged over the surface, causing air to be taken into the mixture. Various types and speeds of cones are used to introduce the air and ensure its intimate mixing with the sewage and activated sludge. The two previous processes introduced air by surface agitation, but in the diffused air activated sludge process, compressed air is introduced at the bottom of the aeration channels through diffuser domes. The domes produce fine bubbles of air, which encourage both absorption of oxygen and the mixing of the sewage and sludge. In these and other activated sludge processes, final settlement must also follow. The final effluent passes over the weir to the river, while the activated sludge is continuously drawn off from the final tanks and returned for reuse in the process. This is only one of the many uses for pumping plant in water pollution control. Activated sludge, surplus to requirements, is returned to the works inlet. Another activated sludge process developed in Holland is the Pasveer oxidation ditch. This is an extended aeration process. The surface aeration is created by a rotating stainless steel brush, the TNO rotor. A mixture of the returned activated sludge and macerated raw sewage is fed to the ditch by way of a V-notched trough to give even distribution. The crude sewage has first been partly purified as tank effluent and then, after biological treatment, as final effluent. The suspended solids have been reduced from 350 to 90 and then to 30 milligrams per litre. The biochemical oxygen demand has been reduced from 400 to 270 and then to 20 milligrams per litre. Sometimes, however, tertiary treatment is necessary. One method uses the micro strainer. Fine suspended solids are removed by passing the effluent through a fine stainless steel mesh, which reduces the suspended solids to below 10 milligrams per litre. This may be required when the river is to be used for water supply. Another tertiary process is the rapid gravity sand filter. Effluent is passed through beds of graded sand, which filters out the fine suspended solids. The process can be automated. The sand filter is cleaned by air scouring and backwashing, and the released solids are returned to the sewage flow. All this care ensures the safety of the river, but a colossal task still remains: the disposal of the waste matter removed during the treatment processes, which is mixed with many times its own volume of water. At a few coastal places, the sea provides a dumping ground, but elsewhere, a large part of the problem consists in reducing the moisture content of this sludge so as to greatly reduce its volume for handling. Where large areas of land are still available, the wet sludge is pumped onto land to dry and to be ploughed in. At many sewage works, drying beds are constructed, but since most of the drying depends on evaporation, this needs a long time in our damp climate, and a large area of land is again required. The sludge dries down to a thin layer, which is carted away for storage. The tedious work of lifting a large area of a thin layer of dried sludge can be obviated by the use of a machine designed specially for the purpose. Channels cut by the machine in the wet sludge serve to accelerate the drainage of water. When the sludge is dry enough, a whole bed can quickly be lifted, and the sludge conveyed to a tip. The surface of the drying bed is left in a good condition, ready for more wet sludge to be run on. The smell of raw sludge is objectionable, and other methods have been devised for urban areas. One process is to de-water the sludge in filter presses. The sludge is mixed with chemicals to ease the separation of water. One chemical is ferrous sulfate. And another, hydrated lime. These chemicals are mixed with the sludge in a tank using a picket fence mixer. Other chemicals used are aluminium chlorohydrate and various other coagulants. After the chemical pre-treatment, the sludge is forced at a pressure of about 80 to 100 pounds per square inch, 600 kilonewtons per square meter, into the filter cells, from which water escapes through a filter cloth. During a few hours, a reduction in moisture content from 95% to between 50 to 65% is made by loss of water from the sludge. The actual figure depends on the type of sludge and the method of treatment. The discharge of filter cake from the press can be automated, and on removal, the sludge cake is dry enough to be carted to the tip. In the vacuum filtration process, a layer of treated wet sludge is collected on the outside of a rotating drum from a trough in which sludge is agitated. Reduction of pressure below atmospheric inside the drum encourages movement of the water through a membrane, which in this case is of textile. The thin layer of dried sludge is removed from the drum, assisted by an increase of pressure at the discharge section. An alternative shown here is to use stainless steel coils, for which less maintenance is required, since filter cloths can become blinded with sludge particles. In a few minutes, reductions from 95% to approximately 75% moisture content is achieved. In certain cases, use is made of a biological process in treating raw sludge, a process which is known as digestion. The process is normally carried out at a temperature slightly lower than that of the human body. Because of the large volumes of sludge to be treated, the raising of the temperature, even to this low figure, requires a considerable amount of heat. The biological changes give rise to the evolution of sludge gas, which is used for heating. The digestion process is first carried out in closed tanks, where conditions encourage the growth of anaerobic bacteria. The floating roof is used to collect the gas, and can also carry a circulating pump which mixes the contents of the tank. Sludge is drawn up the central tube and is discharged over the surface. This also assists in reducing scum formation. The digested sludge can be drawn off from the bottom of the tank. Anaerobic bacteria break down fats, proteins, and carbohydrates in the sludge, producing sludge gas which contains about 65% methane and 35% carbon dioxide. The gas is used for heating, or in dual fuel engines for power generation. The digesting sludge has an average detention time in the primary tanks of 3 to 4 weeks, and is discharged into the secondary digestion tanks for a further period, where separated water is decanted. Another method for conditioning sludge is the heat treatment process. The sludge is first thickened in a consolidation tank. It is then passed through macerators and pumped under pressure by ram pumps to a heat exchanger, where it is preheated by the returning processed sludge. Superheated water raises the temperature of the sludge to nearly 200 degrees centigrade in the heat exchanger. The process is fully automatic, and the cooled sludge is passed to decanters before being fed to filter presses. It is becoming increasingly difficult to find sites where dried raw sludge may be tipped. Due to the nature of industrial wastes, the sludge may not be suitable as a fertilizer in every case, and more drastic measures may have to be taken. The dried sludge is pulverized and conveyed to a furnace for incineration. In many cases, however, the sewage sludge contains, besides humus, useful quantities of nitrogen and phosphorus, with trace elements which can serve a useful purpose. When composted with pulverized refuse, which itself contains these valuable materials, an effective soil conditioner can be formed. The waste material from our homes and industries can be turned to valuable use in our farms and gardens. It should never be allowed to spoil the rivers of our land. Not only can the rivers provide a focus for many of our leisure activities, but as our standard of living rises, our consequent demand for water will increase. We shall rely more and more on clean rivers for the lifeblood of our civilization.